All right, so now we're going to learn about ACID transactions. And I guess we'll start with this picture because it looks kind of cool. Atomicity. I don't know, how would you say it? Atomicity. Luckily, atomicity.
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 Atomicity. Transactions are all or nothing, right? You don't want to like have a bank transaction where you deposit $400 and it takes your money, but then it never records it. It's like you put your money into the ATM, that transaction succeeds or your money comes back out. Or if I'm going to transfer money to Luis, right? Like when it debits from my account, it needs to credit to his account or the transaction rolls back. It's all or nothing. Atomicity. Okay? So the transaction succeeds or it doesn't. There isn't like a half success because that just screwed everything up. Consistency. Only valid data is saved. Okay. That makes sense. Isolation. Transactions do not affect each other. That makes sense. Like, my bank transaction with Luis shouldn't affect two other people's banking transactions. And durability. Written data will not be lost. That's pretty straightforward, right? Not all that confusing. That's this ACID concept. Now, if we go and we look at this on Wikipedia, there's going to be a little bit more to say about it. But that picture was pretty awesome. In computer science, ACID, atomicity, consistency, isolation, durability is a set of properties of database transactions. Symbolizes a unit of work performed within a database management system against a database and treated in a coherent and reliable way independent of other transactions. Makes sense. Intended to guarantee validity even in the event of errors, power failures, etc. In the context of databases, a sequence of database operations that satisfies the ACID properties, and these can be perceived as a single logical operation on the data, is called a transaction. A transfer of funds from one bank account to another, even involving multiple changes such as debiting one account and crediting another, is a single transaction. So that's the classic example. And then if we look down at these, we're going to see transactions are composed of multiple statements. Atomicity guarantees that each transaction is treated as a single unit, which either succeeds completely or fails completely. And that was the picture, right? Transactions are all or nothing. If any of the statements constituting a transaction fails to complete, the entire transaction fails and the database is left unchanged. An atomic system must guarantee atomicity in each and every situation, including power failures, errors, and crashes. Sounds like a good thing. Consistency ensures that a transaction can only bring the database from one valid state to another. That was what was this? Only valid data is saved. Only valid data is saved. And a state is like the current representation of data at a moment in time. That's like state. What is the state of your bank account right now? Right? Current representation of data at a particular point in time. Maintaining database invariance. Any data written to the database must be valid according to all defined rules, including constraints, cascades, triggers, and any combination. This prevents database corruption by an illegal transaction, but does not guarantee that a transaction is correct. Isolation. Transactions are often executed concurrently, reading and writing to multiple tables at the same time. Isolation ensures that a concurrent execution of transaction leaves the database in the same state that would have been obtained if the transactions were executed sequentially. So one transaction doesn't influence another. Durability guarantees that once a transaction has been committed, it will remain committed even in the case of system failure, power outage, or crash. This usually means that completed transactions are recorded in non-volatile memory. What is non-volatile memory? What is volatility when we talk about storage and memory?
Safe.
Safe, right? RAM is volatile. Whatever's stored in RAM, you turn your computer off, it is gone. Needs power to remember. Solid state drives, hard disk drives, tape drives, flash drives, solid state again, right? That's all non-volatile. Power goes off, the data's still there. That's acid. Transactions are all or nothing. Atomicity, consistency, only valid data is saved, right? So here they said can only bring database one valid state to another, maintaining database invariance. Any data written to a database must be valid according to all defined rules. In computer science, an invariant is a condition that can be relied upon to be true during the execution of a program or during some portion of it. It doesn't vary. It's an invariant. There's a logical assertion that is always held to be true during a certain phase of execution. And isolation, transactions don't affect each other, and durability, written data will not be lost. So that's acid. Not too complicated, right? What is this? Is it a fact? This is a fact, right? Is it worthy of memorization? It's kind of theory, something to know about. Don't really need to memorize it. Why don't you need to memorize it? Just look it up if you ever need to talk about it or reference it. But now when you see acid, like, oh, it ensures acid transactions, you don't have to be like, I don't know what that is. Like, you know what that is. Can't remember the details of it, but yeah, it's just kind of like a theory for databases, right? Like to make sure that they work well and not all that usable. We're here to kind of figure out what, the usable stuff, actually be able to do stuff. So the only thing that's usable about acid is kind of being familiar with it a little bit, so when you read it, you don't freak out. And you're not like, I have no idea what acid is. Right? Now you do. You're all experts in it. You don't need to regurgitate it. You don't need to multiple choice it on a quiz. You just have to be familiar with it, so when you see it, you don't freak out, and you're familiar. It's like something built into databases to make them work well. And if you ever need the details, you can look it back up. Simple. Right? You go to a job interview. Do you know what acid is? Yeah, sure. It makes databases work well. Why don't you tell us about acid? I got this theory about facts. Right? And then you kind of laugh. And they're like, that's funny. And then they hire you because they like you. You don't have to have the right answers. You have to be able to find the right answers and use them. It's like, who really needs to know about acid? Really, like, I just know how to use databases. And then people who build databases need to know about acid.